If you have ever wondered how giant rocks dot the Vancouver area, how Siwash Rock and the cliffs at UBC were formed, please join us for a Vancouver geology talk. David Cook has conducted many tours of the Kitsilano intertidal beach. This year we are doing a virtual presentation for our annual Salmonberry Days Festival. During this Zoom recording, unfortunately, there are two very short periods with a loss of sound.
So this is underlying Vancouver city is the Georgia Basin, which is indicated by this darkened area here. And the Georgia Basin consists mainly of sandstones. This is it in plan, and this is it in cross-section. This is the northwest to southeast cross-section, which is through here. It underlies primarily the Georgia Basin, the Georgia Strait, or Strait of Georgia. Is it correct? I'll start again. This is a depiction, a plan of the Georgia Basin, which underlies Vancouver City. This is a cross-section, a northwest to southeast cross-section through that basin. It overlies the granitic basement, which is this. The granitic basement, which extends all the way up to Alaska. At the Canadian-US border, it is about 4 kilometers thick. Geologically, it consists mainly of sandstones of Eocene to Paleocene Huntington Formation, with some Upper Cretaceous Nanaimo group. They're all sandstones. There's some bands of shale and mudstone and some very small quantities of coal. The base of this sandstone basin consists of a conglomerate. It's called a basal conglomerate. Conglomerate is a sediment consisting of cemented cobbles of rock that has been brought in when the rivers were most active at the beginning of the basin's formation. And you won't see them outcropping anywhere under Vancouver City except on Mount Burnaby. But they're difficult to access, so the best place to see them is beneath the Highway number 1, crossing the Capilano River. There are good outcrops of basal conglomerate there. Let's imagine we're walking along the beach. We're going to see in the top left-hand corner, we're going to see a dike on the Kitsilano Beach. It's in 3 dimensions. You can see it coming up, intruding the rocks, and it crops out as a single line along the beach within the sandstones. The outer edges of the dike are when they come up originally through the rocks, they're hot, so they're going to recrystallize the sandstones as they're intruding the sandstones. So consequently, you get a rim along each side there, a recrystallized sandstone, which is actually a quartzite. So you get a band of quartzite along the outer edge of the dike. So that's the feeder dike, what they call a feeder dike to the basalt flows or sills, which is the next slide to the. So the sandstone itself contains small patches of coal, as can be seen here along Kitsilano Beach. And shales, these are the shales, a minor amount of shales with occasional fossil plants. These are deciduous trees, mainly some coniferous trees. They look similar to plants that are living today, but they're actually about 30 odd million years old. Another rock that we're going to get is the other granites, which have their origin in this coast belt, which extends up to the Alaska border. It's one of the longest and largest features on Earth. It's made of granitic rocks primarily, and boulders of this feature have been brought here by glaciers. Here's an example of one on Third Beach, an example of granite that's been torn out of this structure, rounded off by the glaciers, and dumped here on Third Beach. This is about quite a few thousand years old, left on the beach. This is another one in Jericho Beach Park, which is partly submerged. So in the sandstone, we see what is known as current bedding. You can see the layering as the sand was laid down by the river, but the beds are in different directions. And this is the way that the sand is deposited by the river. It's actually in the form of a mini delta. I'll just have to keep doing that. So as the sand moves across the top, it falls down the sides. So you get an advancing bed like that. So the current bedding shows up like this, which is at an angle to the actual the actual direction of the sandstone. This is the sandstone on Third Beach, and you can see how it's tilted up to the north. And that is due to a process called subduction, which is illustrated here. This is the North American crustal plate, extending from where we are here in Vancouver, right across to the Atlantic Ocean. And in the middle of the Atlantic Ocean, you've got the mid-Atlantic spreading ridge, which is causing it to move from east to west. Here off the coast of Vancouver Island is the Wanda-Fuca plate, which is moving from west to east. So you have the two plates coming in conflict. The two processes take place. The Wanda-Fuca plate dives beneath the North American plate. It's known as subduction. And the mountains of the west coast are pushed up as this plate continues moving to the east. As they're pressed up, like here, this is the mountain. These are the mountains rising here. They cause the sandstones of the Georgia Basin to be lifted up. So consequently, the bedding moves up. This is illustrating the formation of a wave-cut notch and a wave-cut platform by wave action. The waves undercut the cliff, forming the notch like this. Cliff falls and so advances back. The result is a flat wave-cut platform, as seen here. You can see the wave-cut platform in many places along Kitsilano and Stanley Park. This photograph is taken close to Siwash Rock. And first of all, you can see these, what appear to be boulders. These are actually concretions, which are shown here within the sandstone. And as the concretions are eroded out of the sandstone, they form the rocky beaches. This is one concretion which shows the concentric nature of the concretion. So the question arises as to how they're formed. They're formed in position in the sandstones around usually an organic fragment. And probably if you split this, you would find that organic fragment, which may be a fossil. This is one of the dikes that intrudes the sandstones. This one is at Third Beach. These dikes intruded the sandstones about 65 to 98 million years ago. Um, and this one can be seen heading out into the ocean. This is the same dike heading out into the ocean. Okay, so Siwash Rock, how is that formed? How was it formed? This is how it was formed. You have wave action cutting away a cliff face until it isolates a piece of the geology. This is and that, so this is Siwash Rock. This is before the seawall was built. This is as it looks today. It's actually not sandstone, although a rock stack can in fact be any rock, but in this case it's volcanics, parts of a sill which goes through this area. This is an illustration of how jointing takes place. This looks almost like a man-made feature, but is in fact jointing of the rocks, fracturing of the rocks. How are they formed? It's due to tension and pressure. So when this process is going on, the subduction process, it's not constant, it's back and forth. Consequently, you get what are called joint sets in the rock. You get parallel sets, parallel to the, or transverse to the stresses, which are these indicated by these two arrows, and you get these transverse fractures through the rock. Other types of joints are caused by compression. I don't have any illustrations of those, but you can see on the North Shore, you can see many examples of joint sets, two sets at more or less at right angles to each other. In our area, it's the glaciation of North America, which, more correctly, the glaciation of Canada. It consists of two parts. What's happened to the cursor? Got the Laurentide glaciation, which is this area, and it essentially is radiating out from center like so. Then we have the Cordilleran glaciation, which is covering the Western Mountains, the Rockies and the other mountains of British Columbia. And that's even though they occurred at the same time, they were separated a lot of the time by a corridor down between them. This Cordilleran glaciation is essentially a coalescence of valley glaciers. whereas the Laurentide glaciation is not. The evidence of glaciation, I've already described the erratics which were brought from the North Shore by the glaciers, but in other parts of the Vancouver area, we get the quarter sands, which are on this map here are shown with this stippled symbol ahead of the glaciers, which are this here with the cross symbols. And the glaciers pushed the quarter sands ahead of them down Georgia Strait and other glacial valleys as well. And in the final stages, the quarter sands ended up forming Point Grey. It's a very, very unstable land surface and erodes very easily. It formed very quickly a canyon at one point called the Campus Canyon, which is on the UBC campus. It's since been filled in. You can see the human figures down here. It's a deposit of about 300 feet thick.